Hello everybody. In this video, I want to give you guys a little bit of an overview of measuring reaction rates. And the first thing I want to talk about is the difficulty that we have measuring an instantaneous reaction rate. We've already seen that what we can do is make a measurement of the concentration and another measurement of the concentration, and then look at the difference between those 2 points here and divide that by the difference in time that it occurred to measure an average rate. But when we're measuring an instantaneous rate, this becomes a little bit more difficult. And there's really two methods. One that involves measuring the concentration over time very carefully, and then fitting an equation to it, and then using calculus to derive an analytical solution for the instantaneous reaction rate, which is kind of outside of the scope of this class and not often done anymore, because now we have a lot of fancy equipment that can use this other technique that I'm going to describe. And in this other technique, what we wind up doing is we make two measurements really close to one another. So we make a measurement here, and then we make a measurement right over here, and there's some delta T that's involved in that. And then we draw a line that connects these two together as an approximation to our instantaneous rate. So we know that measuring the true instantaneous rate is difficult. It always takes some amount of time to make one of these measurements, okay, because we're going to have 2 points on it. Therefore, what we've actually done is measured an average over a small area, okay, where delta T here is small in relation to the overall time that the reaction occurred. This approximation is pretty good the smaller the time required to make the measurement. So the smaller we can make delta T, the faster we can make those two measurements, the closer the measurement comes to approximating the instantaneous rate. So if I can make two measurements that are very close together right here, then I can get a pretty good approximation to the instantaneous rate by using this method. So now I want to talk to you guys a little bit about using handles for measuring concentration. And the problem is that we can rarely, if ever, measure the concentration directly. That's really difficult to do. Instead, we must measure a property that is proportional to the concentration. And just a little review for us here, we can have something that's directly proportional, meaning that as whatever thing we're going to measure increases, the concentration increases, or indirectly proportional, where as the whatever we're measuring goes up, the concentration winds up decreasing. And we need to know the proportionality constant. We need to know how this relates to the concentration. The good thing is there's a lot of different things that we can measure that are going to give us a measure of concentration. I want to go through a couple of examples with you. So when a reactant or product is colored, we can use spectrophotometry to measure the amount and wavelength of light absorbed. So in a spectrophotometer, we have like a light source. It's going to go to something we call a monochronometer. And you can think of that kind of like a prism. It's actually a more sophisticated device these days, but what it's going to do is it's going to separate out the different frequencies of light and allow us to pick a single narrow band frequency to channel into our sample. So now we know what the wavelength is that we're using, and we focus that into a sample. So this is something that I want to measure. It's like a colored liquid, for instance. and it's going to have some path length b that light is going to take to travel through that sample. After that, it's going to continue on until we get to a detector. There's a lot of different detectors out there, photoelectric cells, and CCD detectors and stuff. Things not dissimilar to what you're going to find inside of a camera to change a light signal into an electronic signal. And we know from our theory that the absorbance, which we can think of as pretty much how much light was absorbed by the sample, is going to equal epsilon times b times the concentration. So b is the path length, and that makes sense. If I increase the path length, it's going to absorb more light because it had more contact with the light as it traveled through. And epsilon is something called the molar absorptivity, sometimes also referred to as an extinction coefficient. And what that is it's going to be a value that's specific to this kind of sample. So I need to know something about the sample. I need to measure the molar absorptivity in order to know, to be able to use this equation to figure out the concentration. And typically what we're going to do that is we're just going to take some known concentrations of our sample. So we're going to prepare some solutions where we know of this stuff that we're interested in analyzing. And we're going to prepare some solutions where we know what their concentrations are. And then we're going to measure their absorbance. And we're going to be able to plot those along here. And if we look at this, this has the basic form of a line where we have a constant epsilon b and a changing variable c and a dependent variable a, and the intercept of this would be 0. And then we can figure out what this line is. Then I can take an unknown sample and measure its absorbance. And graphically, mathematically, we would plug it into this equation, but graphically, you could just imagine just coming over straight line until I get to this curve, and then following it down until I get to this axis, and this will be the concentration of our unknown. Another example of using a handle to measure concentration would be when an electrolyte is produced or consumed by a reaction. We can measure the conductivity of the reaction mixture. So we've seen that when electrolytes are produced, they increase the conductivity of the solution. And we have little devices called conductivity detectors. It's an electronic device, and it's going to come out to something we call a conductivity probe. This probe has a set distance between two electrodes with a set geometry, and what we're basically going to do is we're going to measure the resistance of this solution, and the resistance is going to equal the voltage, which we're holding constant, and divided by the current, which we're going to measure. The reciprocal of resistance is what they call conductance, and we can calculate that like this, and this conductance is going to have a linear relationship just like absorbance did with the concentration. And we're going to do the same sort of thing. We're going to measure some known concentrations. It's got this nice linear relationship that we can understand really well. And what's really nice about conductance in particular is that this linear range really operates over a really wide level of concentrations. It doesn't really break down when you get really low in concentration or really high in concentration until you're really to the outer levels of concentration. And that's not necessarily true for spectrophotometry. It'll break down pretty quickly as you get more and more concentrated. And we're going to do the exact same thing. We're going to take an unknown, we're going to measure its conductance. We can travel that over to this curve here and then back down here, and I'll know what the concentration is of that sample. Another example that ties into the conversation we had about gases is when gases are consumed or produced by a reaction, the concentration can be determined by holding the temperature constant and measuring the pressure. So if we make the assumption that it's going to behave as an ideal gas, we can measure the concentration, where the concentration is going to equal the number of moles divided by the volume, very similar to our molarity concentration unit, and that's going to equal the pressure divided by the gas law constant and the temperature. The gas law constant is obviously a constant. We said we're going to hold the temperature constant, so this is going to equal 1 over RT times P, and now we have our linear relationship where C is Y, this is going to be our slope, P would stand in for X, and then we would get an intercept of 0. And again, we can graph this out just as we would expect. We're going to get a graph that's going to look like this. We can determine the pressure, come up here for an unknown, and then determine the concentration of that unknown.